Yes.
Yeah, so we will go through a bit of a review of Hilbert spaces, in particular the type of Hilbert spaces, infinite dimensional Hilbert spaces, the type of Hilbert spaces that we will encounter a lot in a lot of the things that Carlos will go through, things like the quantum harmonic oscillators and these things. So we will start, but we'll start very, very basics stuff about Hilbert spaces, the things that you should know. Give the definition of Hilbert spaces, and also another notion called the Banach space, because a Hilbert space is automatically a Banach space, and also because the operators, the bounded operators on a Hilbert space, they also form Banach spaces. And then we'll give some examples about, I think most of you already know examples of finite dimensional Hilbert spaces, CN, for example. But most of you, especially if you're not coming from physics, what you haven't seen is their infinite dimensional cousins, which are important. So we will go through that. So that's hopefully the first session. The second section will go through things like orthogonality, orthonormality, in terms of the vectors on a Hilbert space, basis, dimensions, tensor products, because you need to know a tensor product, if you want to understand entanglement and all this. This is all behind that. Some other stuff like the Riesz representation theorem, which actually you will see actually justifies, the bracket notation of Dirac. This actually, this theorem justifies that the use of it. So it's not necessarily an abuse of notation. So there's some mathematical justification for the Dirac notation. So, and that's done because of the Riesz representation theorem. You will understand this once you we go through the functionals and the dual spaces, linear functionals. And then the final thing that hopefully we'll cover will be around this, the operators, the operator norm, and in particular the type of operators that you need in not just quantum mechanics, but in quantum computation, like self-adjoint operators, unitary operators. And in here, actually, in the context of infinite dimensional Hilbert spaces, you will see physicists use the term Hermitian to say, like, the operators are Hermitian, the ones that are encoding physical quantities, like, say, for example, the energy. But there is some subtlety in that. For a mathematician, these two notions are not the same. What physicists really mean is the operators are actually self-adjoint operators. These are special type of Hermitian operators that have real eigenvalues. So, but this doesn't matter, this distinction in finite dimensional Hilbert spaces. You can be, you can ignore this, but when you deal with the infinite dimensional Hilbert spaces, these two notions don't coincide. A self-adjoint operator is Hermitian, but a Hermitian doesn't need to be a self-adjoint operator. Anyway, these are like subtle stuff that you will come across during the sessions. And then, you will have like the notion of tensor product of operators, because you also need to do this. You also need to understand this. So that's it. So this is a quick wrap up. We have maybe 3 sessions at least we reserve for this, but it's possible that we might stretch it maybe to a 4 lecture. Sorry, Carlos. If necessary. The main thing is really, the main point is to give you some basic mathematical machinery that you need to make you feel comfortable going through the course. Okay. And we are not really optimizing for speed and how fast the lectures come. We are optimizing for the best possible way to making you learn. So that's why we are putting this. And you cannot escape mathematics, not the least. I think most of you coming from quantum formalism, mathematics is essential part of the activities that the learning, the curriculum that we have in the community. So that's it I have to share with you. If you have any question, please feel free to ask.